Okay, I know I've said this before. I always say it. This is my favorite topic, but this is one of my favorite topics. That's like up at the top of the list. This is like top 5, okay? So, and that's intermolecular forces, okay? The intermolecular forces is what gives the physical properties to certain chemicals, okay? So, there's 2 different terms that I'm going to expect you to know the difference between, okay? That's intermolecular and intramolecular. Intra is what we have dealt with in bonding, okay? So it's when electrons are either transferred or shared, okay? So this is going to be, intra is going to be a bond within a molecule or a compound. So let's say a compound. Okay, so this can be molecular or covalent or ionic. Okay, so when I say intramolecular bonding, I'm talking about the bonds between atoms within a compound. Okay, intermolecular bonding is the interactions between molecules, between multiple molecules. Okay, so this is going to be the interaction between multiple molecules. Okay, how I want you to think about this, and here we're talking about forces. We're not necessarily talking about a bond that molecules have. Okay, so let's just think about that for a second. Okay, so if I have a glass of water, okay, so this is H2O. You guys know that I don't just have one water molecule inside of my glass of water, right? My water molecule is made up of billions and billions and billions and billions of water molecules. Okay, so when I'm talking about the interaction between water molecules, I'm talking about, okay, well, if I do have a glass of water, how are each of those water molecules interacting with each other inside of my glass of water? Okay, and that's what intermolecular is talking about. Intramolecular would be the bond between the oxygen and the hydrogen within the compound. Okay, so this would be intra, these would be inter. Okay? Okay, so here I have a little asterisk here. Intra is going to be the strongest since it's an actual sharing of electrons and the atoms are actually bonded together. Intra is not as strong as inter, or I'm sorry, inter is not as strong as intra because they're not transferring electrons. Okay, so let's think for a second. What happens when we boil water? Okay, well, when we boil water, what we're doing is we're applying energy. Okay, we're applying a heat source to water. And what you're doing is if those water molecules are really close to each other, okay, and they have a force between each of them, what you're doing when you boil that water is you're breaking that force between the water molecules, and what eventually ends up happening is, under my water, okay, is I'll have some water molecules down here, but then I'll also have some water molecules evaporating out of the substance, okay? So this water molecule no longer has an intermolecular force with these 2 water molecules because the heat moved them fast enough to break that force, okay? There are going to be 3 major types of intermolecular forces that exist between neutral, which means no charge, molecules. So like H2O is a neutral molecule, okay, because there's no charge on it. Okay, and those 3 forces that we're going to be talking about are dipole-dipole, London dispersion, which is also known as LDF, and hydrogen bonding. And I don't like that it says hydrogen bonding because that makes you think that there's bonding going on, but there's not. It's just a force. Okay, these 2 right here are known as van der Waals forces. Okay, so if I refer to van der Waals forces, you know I'm talking about dipole-dipole and London dispersion. Okay, so let's get down to this. Let's see what we're going to be talking about here. Okay? The first intermolecular force that I'm going to talk about is an ion dipole force. Okay? So you see the word ion in this intermolecular example here. Okay? And you know ion means charge. Okay? So the intermolecular force that I'm talking about here occurs between an ion, so positive or negative charge, and the partial charge of an atom within a molecule. Because remember, if we have a molecule, we don't have full charges because they're sharing electrons. Okay, so an example that I have here is water, okay, with oxygen having partial negative and hydrogen being partially positive. Notice how these are separated by a dashed line. The dashed line means that they're not sharing electrons. You see these lines here? They're not dashed. They're sharing electrons. So again, just to be clear, this is intra, this is inter. Okay? So you'll notice that the partial charge on hydrogen is going to have an intermolecular bond with chlorine that is negative charged, and oxygen with its partially negative charge will have an intermolecular force with the sodium ion. Okay, so let's think about this for a second. If I was to put calcium nitrate and CH3OH, which is methanol, into water, which one do you think would form an ion dipole? Now I'll go give you a second to think about it. Well, I hope you said calcium nitrate, because if you remember, calcium or nitrate doesn't form a solid in water. It's always soluble, okay? So then that means that I will have a calcium +2 and a nitrate -1 in water. So that means I will have ions. If the ions are present, water is there, I'm going to have an ion dipole force, okay? Good. The next one is a dipole-dipole force, okay? A dipole-dipole force is between neutral polar molecules, okay? So let's break this guy down here for a second. Okay, so neutral polar molecules. Neutral means no charge. Okay, so I don't have a positive or a negative. And then polar, you remember, means that I'll have a partially positive and a partially negative charge. Okay? Okay, so let's think that, and if we want to use more practical terms, I'm going to say that it has a dipole moment. Okay? So they are attracted to each other when the positive end of one molecule is near the other end of the other, okay? So this is going to be weaker than ion dipole forces because they are attracted to each other, but you don't have a fully positive and a fully negative ion in the solution. You just have partial charges, okay? So again, notice the difference between your dashes and your solid lines. Dashes mean inter, solid lines mean intra. So intra is within the molecule, inter is between molecules, okay? So for example, if I have iodine and chlorine as a compound, okay, chlorine is going to want the electrons more, so it'll be partially negative. Therefore, when I have another molecule of ICl, that Cl is going to be attracted to the partially positive of the other molecule, okay? So this is going to be a dipole-dipole force. A dipole-dipole force occurs between all polar molecules, okay? All polar molecules will have a dipole-dipole force. Okay, I think that's all I want to say about that. Let's see. Oh, I do have one more thing I want to say about that. Molecules of approximately equal mass and size, their strength of their intermolecular force will increase with increasing polarity. Okay? Why? Because as you increase polarity, you're increasing your negative and your positive charge, which means you're getting closer to being like an ion. Okay? The closer you are to being like an ion, the stronger that you're going to be. Okay? So if dipole-dipole occurs between polar molecules, I need a force that occurs between non-polar molecules, meaning we don't have a dipole. Okay? So no dipole means everybody is equal. Okay? So between an LDF, think about this for a second. Atoms have electrons. Electrons are free flowing. Okay? Electrons can move within an atom, which can cause a momentary dipole, meaning one side of the atom could be partially positive and the other side of the atom could be partially negative. So for example, if we look at this image that I have here for you, if we have a helium atom, okay, it has 2 electrons in its atom. If the electrons move to one side of the atom, that is going to make that side of the atom more negative than the other side of the atom, okay? So when those electrons are more dense on one side, that means you have a momentary dipole within a polar atom, okay? And you can kind of see that here, that it's going to give us an instantaneous dipole, which then means if I have another helium atom next to it, its electrons are going to be attracted to the positive side of the helium atom, okay? Now it's important to note that this force only occurs if the molecules are close together and they're forced to interact with each other, okay? One other thing that I want to talk about is polarizability, okay? So polarizability is basically how easily can the electrons move from one side of the atom to the other, okay? So let me get that down for you guys. Okay, so again, polarizability is the ease of the electron to move within the electron cloud, or the atom. It allows better dipole moments. So if the electron can easily move to one side or the other side, we're going to say that it's going to have high polarizability, okay, because it can easily become polar. So therefore, atoms that are larger will have larger polarizability due to their electrons not being as attracted to the nucleus, the positive centered core, okay? So if the electrons are way far away from the nucleus, they're able to move more away from one side or the other, okay? All right, so a couple of other things I want to talk about. Dispersion forces. Again, dispersion forces are your dipole-dipole polar molecules, LDF or London dispersion nonpolar molecules. Forces will increase with increasing mass, so you have to remember, especially if you're taking physics or have taken physics, force is equal to mass times acceleration. So the more mass you have, the more force you will have, okay? Shapes also affect forces. If you have long linear shapes, they tend to have stronger forces. Think about a big piece of Velcro. It's really hard to pull it apart, okay? And then dispersion, so dipole-dipole or London dispersion forces will occur between all molecules. Okay, last thing, most important bond, okay? And we'll talk more about this in class, but hydrogen bonding occurs between a hydrogen attached to a NOF atom, so a nitrogen and oxygen or a fluorine, and it interacts with another NOF on a separate molecule. Okay, so let's look at an example. I actually have a couple of examples here. Okay, so this is water. So when I put water, or when I have a glass of water, this is how my water molecules are interacting with each other. Okay, so here we go. Hydrogen attached to a NOF, so oxygen, interacting with another NOF. Okay, so hydrogen, so it's going to have to go NOF, hydrogen, NOF in order for it to be a hydrogen bond. Let's look at another example. Okay, so again, dashes mean not bonding. So here we go. NOF, hydrogen, NOF, hydrogen bonding. Okay, let's look at another one. NOF, hydrogen, NOF, hydrogen bonding. Okay, so that's the order that you have to have in order for it to be considered a hydrogen bond. Why a hydrogen bond is stronger than all of the other bonds besides ion dipole that I've talked about? Because it deals with your NOFs, which have high electronegativities. Okay, and then the last thing I want to talk about or show you is this kind of web that you can use to figure out which sort of substance or which sort of intermolecular or intra, because ionic is on there as well, force that you'll have within a molecule. All right, we'll practice this in class tomorrow. Thanks, guys.